Jai Hind to all of you. I am Dr. Gaurav Saxena. I am an associate professor in EC department, and today I discuss the emerging domain in electronics and communication engineering subjects. So the code is BEC 101, and today I discuss Unit 1, which is associated with semiconductor diode, and what is the depletion layer, what is the VI characteristics of ideal and practical diodes. Today I discuss what is the diode equivalent circuits, what is the Zener diodes, and what is the mechanism of Zener diodes in Zener breakdown and avalanche breakdown. So this is a textbooks which I used to prepare this PPT. First one is Robert L. Bolested and Louis Neschleski, and this is a Pearson publication, which is very good book, and this is recommended by AKTU. So my first topic is semiconductor diode. So what is the basic semiconductor materials? So how we can say this is a semiconductor materials? So semiconductor materials basically two types. First one is direct band gap materials. So direct band gap and semiconductor materials and indirect band gap semiconductors. So the diodes to be formed by both of the materials, which one is indirect band gap and direct band gap. What is the meaning of indirect band gap? So if the momentum K and energy band gap, or that means the valence band and the conduction band, this is the conduction band, which are in same momentum, so we can say this is a direct band gap material. So direct band gap material are also called a compound materials. Compound material, that means which one is gallium arsenide, gallium indium phosphide. So this is the direct band gap material. And what is the indirect band gap material? If the valence band and the conduction band, which are not in same momentum, so we can say such material is called the indirect band gap material. So indirect, what is the example of indirect band gap material? Which one is germanium and silicon? So this is characterized, whole the semiconductors to be characterized in the two form. First one is indirect band gap material and direct band gap material. And what is semiconductor? So semiconductor are a special class of element having the conductivity between the good conductors and insulators. So we can say such material is called the semiconductor. So what are the semiconductors? This is the germanium silicon is the indirect band gap material, and this is compound material, or also we call this is a direct band gap material. So this is a direct band gap material, and germanium silicon is the indirect band gap material, where indirect band gap material where the valence band and the conduction band which are not at same momentum. So what is the history behind that? So diode first to be invented in 1939, and the using of germanium. So first diode which have to be used in germanium in 1939. Transistor was invented in 1947, which is also made from the semiconductor germanium. And in 1954, silicon was used, transistor, because silicon is less temperature sensitive and abundantly available. So that means the silicon's diode is basically we have to be utilized where we used a temperature sensitive material we have to be utilized. And if we want a high speed transistor, so we used a gallium arsenide based diode, because gallium arsenide is a compound material or direct band gap material. So such the conductivity, or we can say the mobility of that particular materials having high, that means 5 times high of direct band gap materials is to be the mobility of high 5 times from indirect band gap material. So that means if we use a direct band gap material, so the mobility of that particular electrons, which one is high with respect to the indirect band gap material. So that means if we want a faster devices, so we use a direct band gap material, because the mobility, we know that the drift velocity, which one is equal to the mobility and multiply electric field. So if the mobility of that particular material is to be high, what is the significance behind that? If we applied a same electric field to that particular diode or transistor, so the drift velocity is to be high. So if the drift velocity of that material or that particle is to be high, so that means that devices to be high speed devices. So if we utilize any transistor or diode for a high speed purpose or high frequency purpose, so we used a mixed material or direct band gap materials, just like a gallium arsenide or gallium indium phosphide. So silicon germanium is a indirect band gap material and gallium arsenide is the direct band gap material, which utilize for high speed or low speed application. So what is the atomic structure of germanium and silicon? So we know that the germanium having a 32 electrons in the so the valency is 4, so 2 electrons, then 8 electrons, then 18, then the outermost orbit we have to be given if only 4 free electrons. So we can say this germanium is a semiconductor diode. But in the silicon, the 14 orbital electrons, which is tetravalent impurity, we have to be utilized for that particular examination. So we have to see that the two, what is the configuration? 2, 8, 4. So that means in the outermost orbit, 4 electrons has to be valence. So that means the 4 valence electrons to be utilized to become a N type of P type materials. So we can say this is a semiconductor material. What is the atomic structure of gallium and arsenic? So gallium, in the gallium we have to be this is a 31. What is the value of this? So we utilize just like a outermost orbit, we have to be just utilize that 3 valence electrons. So and arsenic 5 valence electrons. So this is the extrinsic semiconductor which has been utilized to making a N type of P type materials. So if we utilize a gallium with germanium or silicon, so that means, so in this field, so the holes are to be majority carrier, because they conducting a bond, just like a, you have to just see that this is a pure intrinsic material, pure silicon material. They share a bond between the adjacent silicon, which one is, you have to see that this is a covalent bond. This is a pure semiconductor material, pure silicon. So if we having a impurity, if we adding a impurity of arsenic, so what is the arsenic? Arsenic having a impurity of, you have to just see that what is the meaning of arsenic. Arsenic is a 15 group material. That means the outermost orbit 5 electrons is here. So that means one more additional electrons we have to be utilized. So that means they produce as a N type material, because the majority of carriers which is electrons in this compound materials. So we can say this is a intrinsic, not a intrinsic material, this is a extrinsic material. So what is the energy level? So energy level, the farther the electrons from the nucleus, the higher is the energy state. So in the germanium having a higher energy, binding energy with respect to the silicon, because germanium having its uh, you have to just see that germanium having a 32 electrons. So that means if we escape this electrons, so the binding energy is less. In this case the binding energy is less, but in this case the radius between the, or we can say between the last orbit or valence electrons between the nucleus, which one is less than the germanium. So we can say the binding energy of silicon is greater than the binding energy of germanium. So this is the periodic table. So we utilize, if we want a extrinsic semiconductor n type, so we add a impurity of pentavalent material. So pentavalent material, what is pentavalent? Phosphorus, arsenic, antimony, which has to be generally utilized to making a n-type material having a valency of 5. But if we want a p-type material, so we utilize a aluminium, boron, or gallium, indium. So this one is the this one is trivalent material, and this type of extrinsic semiconductor is typing a p-type material. So we can say if we utilize a 13 group material, I can say having a last orbit electrons is 3, because the 13 is to be utilized by 2, 8, 3. So this type of impurity is to be added in the intrinsic semiconductor. So this produces a extrinsic p-type material. So what is the meaning of majority and minority carriers? So two currents through a diode, एक majority carriers and minority carrier. If we implant a diode by utilizing a p and n junctions, so p-type impurities to be added here, n-type impurities to be added here in a germanium or silicon's diode. So in the majority carriers, in n-type materials are electrons. So that means in the n-type, the majority carriers are electrons, but in the p-type, majority carriers are holes, and the minority carriers are opposites. In n side, the minority carriers is holes and majority carrier is electrons. So in the n-type material, the majority carrier is electrons and the minority carrier is holes, because this n-type also material is called the donor materials. So because the donor ions is plus and the acceptor ions is negative, so that means in the p-type material is also called a acceptor ions material, or in this case p-type material, minority carriers is electrons and majority carriers is holes. So first example of semiconductor material is p-n junction diode. So what is the meaning of p-n junction diode? If we implant any germanium or silicon intrinsic semiconductor, then if some of the portion is to be implanted by p-type and n-type, so this type of device is called the p-n junction diode. In p-n junction diode, the some holes and electrons in the that side, where p side is the holes is the majority carriers, and n side electrons is the majority carriers. And this is ions, this is the immobile ions. In n side, this is the acceptor, and p side is the donor. So that means here you have to just see that they also produces some electric field from plus to minus, or we can say this is a potential barrier. Where, what is the meaning of depletion region? A depletion region is the region where no mobile charge is to be appeared. So we can say this region is called the depletion region. So this is the symbol of p-n junction diode, having a diode voltage Vd and the current is Id. Diode basically conducted in the two parts. First one is forward bias and second one is reverse bias. In the first case, if diode, this is the symbol of diode, this is p-type material, this is n-type material. If we p-type material is to be conducted to the plus and n-type conducted to be the negative side of the battery, so we can say this diode works as a forward bias. In the forward bias, the ideal diode is to be work as a short circuit. What is the meaning of short circuit? The resistance which is very low. Resistance is ideally to be 0 ohm, and ID, the diode current should be maximum or infinite. So we can say if the diode should be ideal one, then the PN junction diode works as a short circuit. But in the case of reverse bias condition, when p-type terminal is to be connected to the negative side and n-type connected to the positive side, so this arrangement is called the reverse bias manner. And in this case, the resistance, they produce a high resistance, or we can say open circuited, or we can say this no current flow. That means in the open circuit, the diode current should be 0. And how we explain the diode, PN junction diode working principle by using the 3 condition. First one is the no bias. That means if PN junction diode is not connected to the any battery, so first reason is no bias. Second one is if p-type is to be connected to the plus terminal and n-type is to be connected to the negative terminal, so we can say diode works in the forward bias condition. But third case is, this one is second case and this one is third case. If p-type terminal is to be connected to the negative terminal of the battery and n-type connected to the plus of the battery, so this connection is called the reverse bias connection. In the reverse bias connection, ideally no current flow. That means ID should be 0 and the resistance between them, which one is infinite. But in this case, forward bias RD is equal to diode resistance is 0 ohm and maximum current flow, or we can say diode should be short circuited and the diode current should be maximum. So this is the working principle which I already explained. So this is the VI characteristics of PN junction diode. So what is the meaning of VI characteristics? So VI characteristics, what is the diode voltage and the relation between the diode voltage and diode current is called the VI characteristics of diode. So if we vary the input voltage, so diode across the voltage across the diode is to be varied independently. So that means the diode voltage is to be varied independently. So diode voltage is called the independent variable, and by varying the diode voltage, diode current according to them, so diode current is the dependent variable. So if we plot a IV characteristics, so always independent variable on the x-axis and dependent variable also be taken in the y-axis. So that means diode voltage is to be taken in the x-axis and the diode current is to be taken in the y-axis. And we plot IV characteristics in forward bias. So this one is forward bias. When diode works in the forward bias, then P is to be connected to the positive of the battery and N is to be connected to the negative of the battery. That means the diode initially the diode not working because of the cut-in voltage, because of the internal potential barrier. Internal potential barrier. What is the meaning of internal potential barrier? For silicon case, this one is 0.7 volt internal potential barrier, and germanium, this one is 0.3 volt at 23 degrees centigrade. So in this case, this is a germanium diode. So I just taking a germanium diode. So you have to just see that after the 0.3, the current increases rapidly. So this 0.3 voltage is called the cut-in voltage for that particular diode, or this is a knee voltage. Also we called a knee voltage. Cut-in voltage, knee voltage are same. And this is the diode current. So if we curve fit this graph with respect to the VD and ID, so we utilize some equations where this is called a diode equation, or p-n junction diode equation, where ID is the diode current, IS is the reverse saturation current in the reverse bias manner, and VD is the voltage across the diode. Eta is the equality factor. For germanium which is 1 and silicon which is 2, and VT is the threshold voltage which is dependent upon the what is the temperature at that particular instant, where VT is equal to KT upon Q, where K is the Boltzmann's constant, T is the temperature in Kelvin, and Q is the charge of electrons, which one is 26.3 millivolt. So if we put it, so we easily calculate the diode voltage at particular diode current at particular voltage VD. So I already explained this. So what is the cut-in voltage of gallium arsenide diode? So gallium arsenide, this is a compound material, or we can say this is a direct band gap material. The forward voltage or cut-in voltage, which one is 1.2 volt. What is the meaning of this? If we utilize gallium arsenide as a diode, so if we want that particular diode to be conducted, so we apply a 1.2 greater than voltage across the diode, then they conduct. So we can say this is a cut-in voltage or knee voltage. For silicon, this one is 0.7 volt. For germanium, this one is 0.3 volt. So this is the comparison of germanium, silicon and gallium arsenide. So we easily differentiate by their cut-in voltage, because the germanium having a cut-in voltage 0.3 volt, in silicon this one is 0.7 volt, and the gallium arsenide which one is 1.2 volt. So we easily differentiate in forward bias manner how we utilize these diode. If we make these diode by indirect band gap material, just like a germanium silicon, or direct band gap material gallium arsenide. And this is the reverse. This is the characteristic or in the reverse bias, or we can say how much current is to be flow. The breakdown voltage which is greater than gallium arsenide, which is highly high. That means the reverse breakdown voltage, where if we increase the reverse bias voltage across the diode, so at any instant point the heavy current flow, that particular voltage is called the reverse bias voltage, where the heavy current flow in the reverse bias manner. So that particular voltage is called the reverse bias voltage. For gallium arsenide, it is greater than the silicon and germanium. So third one is, what is the temperature effect on VI characteristics? So we know that the temperature effect, the VT upon dt, which one is equal to minus 2.5 millivolt per degree centigrade. So what is the significance behind that? V threshold, that means this is not a V threshold, this is a cut-in voltage. So that means if we increase the temperature, suppose this is a graph on 25 degrees centigrade. So if we increase the temperature by 5 times, and this experiment is going on at 125 degrees centigrade, so that means the temperature rising is 100 degrees centigrade. 25 to 125, that means the temperature rise in 100 degrees centigrade. So that means if we multiply by this millivolt to 100 degree, so that means which one is 250 millivolt minus, that means minus 0.25 millivolts. So what is the meaning of minus sign? That means the threshold voltage to be decreases. If suppose this one is 0.7, so new threshold voltage or cut-in voltage is 0.7 minus 0.25 volt. So that means 0.45 volt at, this is the cut-in voltage of silicon diode at 125 degree centigrade. So you easily calculate what is the cut-in voltage at different temperature. So in other case, if we decrease the temperature by 100 degree centigrade, that means the initial temperature is 25 degree centigrade, and we decrease the temperature at point minus 75 degree centigrade. So that means we decrease the temperature by minus 100 degree centigrade. So that means minus minus plus. So this one is plus 0.25. So the new cut-in voltage for this silicon diode at temperature minus 75 degree centigrade, which will be plus 0.95 volts. So that means this voltage is 0.95 and this one is 0.45. So if we increase the temperature, so the cut-in voltage to be decreases, and if we decrease the temperature, so the cut-in voltage for silicon diode or germanium diodes to be increases. So irreversible proportional is to be maintained. So next topic is what is the diode equivalent circuit. So diode equivalent circuit is to be modeled by three models: piecewise linear model, and the simplified model, and the ideal approximation model. This is the simplified model, or this is a piecewise linear model. So this is a piecewise linear model, this is a diodes, and if this is a silicon diode, so we model this diode by this cut-in voltage. This is the internal voltage, we have to be applied by plus ions to the negative ions, and this is the diode resistance in forward bias, which one is very low in the range of 10 ohm, and this is the ideal diode symbol. So that means I already explained to you. So this is the 0.7 cut-in voltage, and that means this is the IV characteristics of piecewise linear model having a R average. How we calculate it? Average is the resistance R average, which one is delta V upon delta VD upon delta ID. So we calculate this. What is the value of this? This is 0.8, and what is the value of this? Which one is 10? So we easily calculate what is the average resistance of that particular diode by using the piecewise linear model. So this is the simplified version. So because if resistance load is in the range of kilo ohm or mega ohm, and the diode resistance in the range of ohm, few ohms, 10 ohm. So with comparison to the network resistance, this diode resistance in forward wire, which one is very much less than, so we ignore that. So that means the resistance should be, diode resistance should be 0 ohm in simplified model. So what is the meaning of this? If the resistance is should be infinity, so what is the ratio of I upon V? This is the conductance. So that means the conductance should be infinity. फिर I upon V ratio is to be infinity. That means tan theta is equal to infinity. So theta is equal to 90 degrees. So that means they making a slope of 90 degree if the average resistance should be 0. And this is the cut-in voltage 0.7 for silicon. So that means the simplified version is 0.7 and having a huge current is flowing in that particular direction. Thank you. So today I have to be just giving a brief idea of PN junction diode, and the next slide we have to be confirmed to be I just utilize what is the ideal approximation model of PN junction diode, and you have to just give me these books. these books is, the name is Robert and Bolstead. So you just utilize these books to making this PPT, and you also, thank you.